Assalamualaikum. My name is Muhammad Nazir Haziq bin Muhammad Nasib, and my supervisor is Dr. Noaini Muhammad Noor. For my FYP project, I will present about study on sugarcane bagasse activated carbon for use in energy storage. Okay, first we talk about sugarcane bagasse. Sugarcane bagasse is a waste after the sugarcane being pressed to release the juice, and usually sugarcane is used for a fuel for heating water boiler. But for this project, for my project, I will use it to produce activated carbon by using pyrolysis process. As you can see, this is the sugarcane bagasse. Consists of three main components, which is from polymer, cellulose, lignin, and hemicellulose. Next, I will talk about the activated carbon that we want to produce. This is some example of the picture. The first is contain a large surface area, and its structure is porous, and there is a fact which is 1 gram of activated carbon consists of 3000 meter square surface area. Also, this activated carbon can be used in energy storage as electrode. This is because it contains high capacitance due to its high surface area. Okay, next is the public statement. Materials for electrode. Usually, electrode that used in the supercapacitor is metal. But metal have so much problem. For example, the metal can be dissolution, which means it's easy to corrode, and also its lifespan is quite low if we use it frequently. Also, next is the preparation is tedious, which is difficult to prepare a metal to produce electrode. And lastly is high cost. So to tackle this problem, my project will use activated carbon for the electrode. Okay, this is my objective. The first objective is to produce activated carbon from sugarcane bagasse by using pyrolysis method. Second is to characterize the properties of activated carbon produced from different set of parameters. For my project, we focus on molarity. Okay, now is the literature review. For first is sugarcane bagasse. Production. From the production is about one wet ton of cane processed at the mill will produce approximately 280 kg of sugarcane bagasse. This example is taken from Brazilian sugarcane. For the composition, sugarcane bagasse, the main material is cellulose, and followed by hemicellulose and lignin, and lastly is pectin. Next, the teacher review is about activated carbon, which is it consists of two processes, which is physical activation and chemical activation. As you can see, the first step is the same, which is the carbonization at 600 or until 900. Between that, which means that we burn we heat the material until it become carbon. For this one we use waste. Next step is different. For physical activation, the carbonized material will be exposed to oxygen at 600 or between 600 and 100 and 1200 degrees Celsius, which is the temperature is quite high. But for chemical activation, we need to recarbonize at 450 temperature degrees Celsius, which is more low than physical activation. But they need to use activating agent like phosphoric acid or sulfuric acid, potassium hydroxide or zinc chloride. For my project, I will use chemical activation because it's require less energy than physical activation, and also it's the chemical activation will produce activated carbon that better quality than physical activation, more porous, bigger surface area. Next is the flow of the process. Okay, first I need to crush and grinding the sugarcane bagasse, and then I will produce a KOH solution, which is the activating agent. Next I will mix the activating agent KOH solution with the sugarcane bagasse. After that I need to dry it to remove any contamination, and then I will heat it with pyrolysis process by using the furnace on this picture. This is the furnace that I use. It is pyrolysis process, so it need to be inert. So we apply for my project, I apply argon gas into the furnace, and then after we pyrolysis, the activated carbon produced. Next will be characterize the activated carbon. Okay, for next part is the sample preparation. First is the raw sugarcane bagasse. I obtained the sugarcane bagasse from the local store, and then I wash it and dry it to remove any contamination, and then grind it to make it a very small particle, and then I characterize it to study the structure, and then I will mix it with KOH solution. Okay, next is how to make the KOH solution. First I got the KOH physical. The activator that I use for my project is KOH, which is potassium hydroxide. I got it on powder form, so we need to change it to solution. So to produce 1000 ml of 0.4 molarity KOH solution is by using this formula, N equal to MV over 100 over 1000. First we need to get the number of mole, so the answer is 0.4 mole. Next we need to find the mass, how much powder of the KOH that we need to produce 1000 ml of KOH solution. So using the formula N equal to mass over molar mass, we can find that the mass is 22.44 gram, which means that about 22 gram of powder are being used to produce 1000 ml of KOH solution. Okay, Next, this is my sample, which is only 3 sample. The constant for this project is the pyrolysis temperature. We use it 650 degrees Celsius, and the holding time is 30 minutes. The parameter and the different parameter of the sample is the molarity of the KOH, which is the activating agent we use with different molarity for each sample. We use 0.4 molarity, 0.8 and 1.2 molarity. Okay, next is the result. First, I will talk about the thermal gravimetric analysis on raw sugarcane bagasse. So you can see this is the TGA of raw sugarcane bagasse. During my FYP1 the last semester, I tried to pyrolysis the raw sugarcane bagasse about 10 gram, and after the pyrolysis I found out is only 2.4 gram left after I pyrolysis, which means that 24% of the raw sugarcane bagasse is produced and it is left. As you can see in the graph, last semester I pyrolysis it on 600 temperature, 600 degrees Celsius, which is about 20% of the mass, which is quite the same as the 24% left in weight, which is almost the same as the graph. If we pyrolysis it temperature in 700 or above, the raw sugarcane bagasse will turn into gasification. We will turn to gas, so carbon will be lost. There will be no carbon in solid form. So for our project is we want to produce activated carbon, right? So we need it in a solid form because we want to make it electrode. Next is the scanning electron microscopy for raw sugarcane bagasse. As you can see, this is the image. You can see it's have a fiber in the surface, long fiber. So, and then the surface is quite rough. As you can see on the right picture, there is a void which is quite long. Okay, next is SEM, scanning electron microscopy for activated carbon, that I have produced. As you can see, the image is very different from the previous, from the raw sugarcane bagasse. There is many porosity produced on the surface. This means that the KOH solution, which is the activating agent, stimulate the enhance of pore, which is help to produce more pore on the activated carbon. 1.2 molarity show a better porosity. As you can see in the picture, the porosity is many. There are many pores in the 1.2 molarity than the others. Although the size is small, but the surface area in 1.2 molarity is more bigger than the others. Next is the Fourier transform infrared spectroscopy for raw sugarcane bagasse, FTIR. As you can see, there is a OH bond 3300 which means that they contain cellulose. Next is 1600, which contain aromatic ring bond, which means that there is a lignin bond. And also 1200 is contain of CO bond, which is also lignin. And lastly is SO double bond on 1000, which is the sulfoside class. Next is the FTIR for activated carbon for each molarity. As you can see, first is same as the Sugarcane Bagasse at the 3100, contain OH stretch. On 2000, about 2000 until between 2000 to 2200, they contain carbon triple bond. On 1600 frequency and 850 frequency, it also contain carbon, which is double bond. This means, as you can see on the table, there is many carbon bond that produce from this pyrolysis process, which we managed to produce an activated carbon. Next is the X-ray diffraction on activated carbon for each molarity. As you can see, the broad peak at the 32 degree here, and also 41 degree here. This graph means this curve means that there are amorphous carbon structure in the sample, which means that the structure is less crystallinity, which is a semi-crystalline. Also with this graph, we can calculate the D value using a Burow's law, which is the interplanar spacing equal to order of reflection times wavelength over 2 times sin theta. The constant is wavelength is 0.154. Is come from the SRD machine, and order reflection is 1. After calculate the D value, we can see that the activated carbon 1.2 molarity contain the highest D value, which mean that it has the biggest space to allow charge to flow in. The D value means that there is a D value is actually a space between plate. It's a space between plane. D value is actually a space between plane of the atom. So the bigger the value, which means more space. So that if for activated carbon, which means that which means that the can create, which means there is a porosity. So if we use it at the electrode as a electrode, which the charge flow can go to the activated carbon because of the space. Next is the cyclic voltammetry CV on activated carbon. The voltage window is between negative 1.5 until 2.2 volt. The scan rate is 0.01 volt per second, which is taken a short time to run this test to complete it. But the drawback is that the graph body is not quite pretty because high noise occur, as you can see here, so much noise. But still manage to get a shape of a quite shape of the graph that we want. The as you can based on the graph, the graph show that 1.2 molarity activated carbon has the biggest area on the graph, which means that, as you can see, it's quite bigger than the graph, the area. This means that it is more better in high capacitance, which is the current or charge can flow through it more easily, more higher, which means that the 1.2 molarity active carbon can be used as a better electrode. Okay, so the conclusion for this project is that sugarcane Bagasse give good properties of active carbon, which is better properties. Is the active carbon that produced consists of good property. Next is the KOH activating agent help to enhance the surface area and porosity of activated carbon. Lastly, after comparing the three samples, it has been shown that the activated carbon with 1.2 molarity shows the best sample for energy storage application. So that's all is for my presentation. Thank you.